Obadiah is only one chapter long. Okay, so let's have you got a whole weekend. You've been revived, like we right? And part of revival is not what you do in the service of revival. Revival is how you live after the service. And I was actually talking because raise your hand if you're part of prayer movement out of curiosity. Oh, that's sad. So,
Are you in revival? I used to be part of that.
how's it going?
No, I used to be.
You guys about part of prayer movement?
I used to be part of
Yeah.
it.
One thing that I was telling my set, and a lot of freshmen, they come in and then we paint this picture of what spirituality looks like. Right? Hey, you're worshiping God when you're in this context. And I went to a set last night, and one of my teammates was there, and he kind of came over to me and just like, all right, like our turn's tomorrow, like we're next. And it kind of breaks my heart in some sense that we've managed to compartmentalize worship to our scheduled designated time. And so I'd encourage you, the same thing I said to him, I encourage you, is that life of worship, whether that's in prayer or prayer movement or worship or revival, isn't really what you do at the scheduled time. Really what you're doing is you're always living in that. And then you happen to sometimes go and do it corporately with other people. So if you're trying to rely on other outside sources to feed you spiritually, you're going to leave here and leave him. Because if you don't put yourself in, if you don't root yourself in following him for your own sake, you're not going to follow him when everyone else isn't. And that's what happens. It's confronted in Luke 9:57-62. Jesus is addressing this issue. People are coming because there's so much hype surrounding Jesus coming, and then does miracles. And in the Samaritan village, they're like, wow, this is fantastic. And so they're all chasing after him because they've seen that he is God. They've seen that he has done miracles, and they even acknowledge that he is God. And then yet he challenges them to sacrifice their comfort, their security, and their will, basically, in following a discipleship. And so all three of them leave. So let's not be the men on the road that met Jesus, right? And we can come to, you're in a classroom where many people have come before, prayed before, you go to chapel twice a week, and you do all these things. You're going to be gone out of here in engineering firms where nobody really talks about God, if anybody knows God, especially in this field, okay? So make sure you have for yourself the relationship with your own God. When you take it out of ORU, you take it to other people. That's where that one goal, one mission is still the same. You're always going to be glorifying God no matter where you're at. And you're always going to be doing that through obedience. All right. So read Obadiah by Monday. Not long. And I think the way we'll do this is, the way we're going to do Obadiah is you're going to read it. I'll read it too. And instead of making the lab 2 due tonight, that would be kind of annoying. So we're going to push this back to Sunday night. Here's the thing though. Just because lab 2 was due on Sunday night, what that means is you're going to do it today as if the Dropbox were closing tonight. And then you just happen to have an extra day of grace to get it done if you had other things going on, okay?
Sunday or Saturday?
Sunday night. But that means start it today as if it's due tonight. So that you have that day of in order to get done. At the very end of your lab, I want a paragraph. Talk to God. Have him talk to you. It just doesn't have to be something you only do in chapel. You can sit and you can listen. It's great. God, what do you want to tell me? And it could be something simple. This doesn't need to be over spiritual. He could just say something like, go to your class. And you're like, all right, amen, Jesus. I'll do that. That's how I'm going to obey and apply the word. Or it might be, stop turning in assignments late and asking for extensions and complaining when professors don't have grace. Okay? Abused grace is no better than extended mercy. So let's do that. So make sense? Add that to the end of your labs. Obviously I'm not grading that because that's a terrible thing to program into people's brains that your spirituality is on, really no. But just do it for your own sake. Because eventually I want to cultivate a habit where you're pursuing this on your own for the own sake, that you do take time in God's word. Yeah.
What if you've already uploaded the lab?
Just send me an email. Yeah. Yeah. Well, if you've already uploaded the lab, that means you're kind of like, what, a type A personality?
I realized it was students yesterday. It was like,
Oh. Hey, but guess what that means? That means you won't be turning it in late, right? Amen. Okay. First of all, I have experienced vast disappointment in past semesters as a teacher here. But you guys
Really just.
killed. When I say my week was made since Tuesday, I tell you, my week has been made since Tuesday. I go to chapel, I say, God, I know revival must be real because class of 23 calculus students showed up and actually put down the work. They studied, they came. Revival is coming in more than just one way. It's coming through these grades and these exams. And no, yeah, I mean, that's crazy. I have never seen the central measure so high. It was like an 88 average in the entire class. That's insane. I think last year it was like either a mid 60 or 70 average. So you guys feel great. I have to give you props for that. I'm so proud of you all. Yeah, and give yourselves a hand. Like that's crazy. Yeah. That's what I'm talking about. That's that one goal. That's that one mission, right? You're taking this, you can glorify God through your grades, not because you probably deserved it at times, but because he helps you anyways. And you spend time with him. Okay, so the lecture is short today because it's easy. And then I actually brought your exams with me today in this folder, so then you'll have time to see what's going on and everything. Because the average is so high, I'm not going to be able to apply a curve. I'm also not going to be able to do like revisions for credit. But I'll talk to Dr. Harder about potentially doing over fall break like some extra project or something for overall points in the exams as a whole. So I'll brainstorm things to do with that. But as of right now, how it sits, it's going to be how it sits because it's been highest it's ever been ever, pretty much. So with that being said, other questions about that before we go into the topic today? Rebecca.
Is there a project in general in Calc 3? Because there was one in Calc 1 and Calc 2. And I was just curious.
Technically no, but I might convert it to the extra credit thing for like getting exam credit, maybe. Yes, boy.
For your previous classes, you said the average was like at 60 something. Was it the same exact exam or was it like a lot harder?
Let's just put it this way. I gave an exam review just as detailed as I gave you guys, and they had the audacity to fail it. Not only was that average, that's post curve average. So your average is raw, the highest raw average I've ever seen in my life. It was after like when I talk, people think that I'm like, your professors aren't trying to kill your grade. Like after every single time someone was able to just read through and get it, it was just people get really annoyed sitting around me when I'm grading because I'm just like, yes, we're rooting for it and cheering you guys on when I grade it. It's really fun to see because that's really at the end of the day, that's all an exam does. It's a measure of how much you've been able to take out of what you've learned and not an opportunity for me to punish you for absolutely no reason. You see what I'm saying?
Yeah.
That's my philosophy on assessment. There is no way for me to tell how much you've actually learned unless you're in that kind of a semi-pressure environment. But then it's really exciting, to see you guys learning stuff. So, anyways, yeah, let's talk about 15.1. It's just basically extending the concept of a function and a graph, and we're escaping the plane. So one might say we're escaping the matrix, breaking the fifth wall, or the seventh or the n+1 wall, depending on how. So let's recall. I'll tell you a little story. And I can't believe I spelled recall with REA. Okay, recall. Everyone, if I said y equals f of x, you're probably just like, oh wow, I haven't seen that. Right? So this is a function, right? And what we don't really always say though is that this is how we state it explicitly, right? So we're telling, hey, when I plot this, whatever's going to go on that y-axis, whatever I'm putting up there is given by this rule, essentially, of this function. But sometimes, okay, so like, for example, this looks like some sort of a function, right? So here's my x-axis, here's my y-axis, and essentially the rule is I put on my y-axis whatever the function is telling me at this certain input. And something that isn't maybe necessarily spoken about directly, but you still are familiar with it, is if we represent it like this, fxy equals 0, or however we want to say it. But the idea is this is giving the function implicitly. In other words, all the variables are smashed on one side. So this would be implicit. And the difference between this would be something like, where if this is a function, we might implicitly define something like an ellipse. Right? Because isn't ellipse a function in R2?
No,
No, then why not?
Because
fails the vertical line test.
Exactly. So this passes the vertical line test at every single x value, but this doesn't, right? We're intersecting it more than one spot. So we can't call this a function, but we can still implicitly define that set of points in the plane. Does that make sense? So explicit has to deal with the function, and we're giving a rule to assign the points that you can graph, whereas the implicit is not a function, but it's giving a description of a set of points that doesn't necessarily have to obey that vertical that vertical line test. Does that make sense?
How does vertical line test apply to 3 dimensions?
Well, let me draw you a picture here. So that's kind of the next natural extension. So if we have y is equal to f of x, I want you to try to see this as here is a real line, right? This is just a set of real numbers, and then we're putting outputs on some other dimension. Now, in 3 dimensions, that input space is now going to actually be the plane R2. In other words, whatever you plug into here is some location somewhere in R2 that you flattened out on the floor. You can imagine that when you're standing up, however tall you want to make your output value is going to start tracing out a surface now in 3 dimensions. So now we say Z equal to F, where we input a coordinate pair from the plane, right? So instead of our input space just being this line, just a single value in R, now we're going to have an input space that's going to be the whole plane, Cartesian plane. And so this is explicit. And here's how we can kind of draw that. So here's my X, Y. This is kind of the plane, right? So we've got space. This is the input space. The same way that this line is the input space for a regular function in the plane. Now, if we have a surface in 3 dimensions, this is going to be the input space. And so when we literally say the y value is equal to whatever gets spit out here, what this is saying is the z value, how tall we are, the z value on this new axis is going to be defined by a very specific x and a y. So depending on what I put in, depending on where I'm at in my xy input space, it's going to be assigned a specific height. Does that make sense? So it's just extending this idea of here's the input, and then the resulting number we stick on a separate axis. Here's now an input. The input maybe involves a coordinate instead of just a single scalar, but the output is still just going to be projected upward to some other axis. So then a surface, kind of like a plane. That could be a function here. Because now, so for every single point input, you can find what it's supposed to be by plugging it into the way. So this would be a plane. So you'd anticipate it to be linear in structure. But this does pass a vertical line test because you take that vertical line, and there's no instance in which if I move this vertical line throughout the surface, that the surface is kind of like fold on itself and intersects twice. So everyone get a sheet of paper, like a piece of paper. Can I borrow this paper for the example? Okay. So underneath this piece of paper could be your input space down here, and this is your surface. Now, this could be a function. However, if I have a surface that does this, if I have vertical lines coming through it from underneath, how many times is it going to be intersecting this surface at certain place? Yeah, that's kind of the same idea as this, that we have a vertical line that's intersecting this set of points more than once. And so would this be a function in R3?
No.
No. Would this be a function in R3?
Yes.
Yeah, why?
Vertical line only touches.
Yeah, every single input point down here is only getting assigned to exactly one 3-dimensional space up in Z. What about this?
Yeah.
Is this still a function?
Yes.
Yeah. What about
Yeah.
Look at that. You know what they should really give me? They should give me like a $4,000 budget just to buy toys for Calc 3 to do these things. Okay, what about this? No, this isn't. And so if you imagine taking, what if I did it like, oh, 3 ways now? No, because now that intersects. But is this still a surface in 3 dimensions now?
Yeah.
Right, is this still a set of points you can have? So just because you have a collection of points in your output space doesn't necessarily mean it's going to be a function, but you could describe it. So for the ones that weren't functions, instead of defining that explicitly, we can define it implicitly. So extend the concept. It's going to be f. What's going to be in here?
X, Y, Z.
Right, x, y, and z all on one side, and that is going to be implicit. Again, that's kind of the main oomph of the section. So thumbs up if this is all good. I'll write the definition box out once everybody's ready.
So does that mean that the ellipse, from the 2-dimension, let's say for example, we were to make 0 in the scale, because it would go up on the axis by like 0.
Are we talking about this one or this one?
I'm saying if we were to take the top one, 2-dimension, and bring it into the z-axis, it would become a function.
Oh, okay, yeah, that's a good point. So if we took this curve and then stick that into kind of like hovering above the point, yeah, that does work. Because then that surface is now satisfying that vertical line test as well. Now, when remember all those quadric surfaces that I told you were obnoxious, but they're kind of useful to visualize what's going on? An ellipsoid, the egg. Okay, is that do we define that explicitly or implicitly?
Implicitly,
Why is it implicit?
because it doesn't pass the vertical line test.
Yeah, it's not a function. Okay, but what about the paraboloid? Can we do that explicitly or implicitly? Yeah, we could do both, but we can specifically do it explicitly, whereas before we couldn't do explicit with a paraboloid. And so that's because when you see that paraboloid, it's going to satisfy that vertical line test, so it's a function. Okay, so not all the quadric surfaces are functions, and but that doesn't mean we don't have a way to describe all of the quadric surfaces. To know the difference, especially when they get picky and Pearson about capital F and that's implicit versus just the axis variable and then the inputs. Okay, let me write out the definition of function. And when I say a definition of function, it's because it technically is a definition of function, but it in one sense is not the fuller picture. So if you want the fuller picture, come to topology seminar Tuesday at noon, and there's we talk about what it really means to map things onto other things. But in terms of what you guys need to know for functions, this will be sufficient.
Scott, if we just tighten the bolts on this whiteboard, would it rock less?
You know, if the plethora of mechanical engineers who are in this room right now and also preceded you did not have the moral or ethical gumption to fix this whiteboard for me in the last 3 years, then I think I'll just we'll see. I mean, I think it's actually missing
got
some parts
sockets?
though. Yeah, I mean, that could be you could be a project.
Senior project.
Senior project.
Make an unshakable whiteboard.
Yeah. All right, everybody, write this down. Definition: a function. A function. I always sound like Sal Khan because I write really slow, so I say it. Z is equal to f x y. Assigns to each point. Assigns to each point x y. And we're going to have a set we call D, and a set D that's contained in the subset of basically the plane R2. So we're going to assign to all of these points a unique, that's important. So that's kind of where the vertical line just comes in, a unique real number. We call that Z, so the Z axis, in a subset of R. So all that means is essentially when you have a function, that doesn't necessarily imply every single value in the new axis is going to be taken account of, right? So if you have y is equal to sine of x, well, the only y values you're really reaching into are from -1 to 1. So that's definitely just a subset of all the possible real numbers you could have had. So that's all this little phrase means, is that you're not necessarily having to cover the entire axis. This is a hint at what the range is going to be. So the set D is the domain. A word that I know you have seen a lot. The domain of our function f. And the range of our function f is the set of real numbers, the set of real numbers then that are assumed as the points x, y vary over the domain. For the domain. That's a lot of words. I think it's kind of ugly. How we would describe this in more algebraic terms is I would say I have a function. But what I'm really doing is I'm taking something from R cross R. So a subset of R cross R. And that is going down and being condensed to a single real number. So if you like this, or just that, take your pick, but this is why I'm a math major. If you want to be more specific, you could call this mapping D onto the image set of the function R, but any questions about this? I mean, obviously it's just extending what you've already seen about functions and ranges and domains before. Good? Okay. So really all we got to do is work on some examples of this and then we can move on to the exam review stuff. Let's see, do I want to erase this or do I want to just use it? Yeah, I'll just do it right here. Okay, so domain, let's do the domain of the function. Let's define a function. It takes two variables, but really I want you to think of this as one input. It just happens to be an input that exists in the plane. And let's call this, we're going to assign vertical points depending on where we're at on the rule 4 minus x squared minus y squared. So 4 minus x squared minus y squared, square root of that. Okay, so this is saying we're going to take a point somewhere in the plane, and then that z value that we pop into 3 dimensions is going to be as tall as whatever this rule gives. Okay, so domain is going to be involving what are we allowed to slam in here without breaking the machine. And so this is a square root. Can we put negative numbers in square roots? No. Okay, so that's kind of a clue. We know that whatever the inside does, right? So the 4 minus x squared minus y squared, regardless of what that actually is, we know it has to be non-negative. Is it allowed to be 0 though?
Yeah.
Yeah, sure. Right. If this is 0, okay, square root of 0 is 0. We're allowed to do that. So it needs to be greater than, and we can also include, so equal to 0. And then now, how we can represent this, if we add the x squared and the y squared to both sides, we get that x squared plus y squared is less than or equal to 4. I really hope that's familiar to you, and if it's not, talk to me after class. So this is what shape?
Circle.
Oh, okay. So if we're thinking about our input space, x, y, and here's z. Now I'm not going to sketch the surface, but we can depict what this domain actually is. Our domain is interested in all of R2. We're not interested in inputting everything because we actually can't put everything into this function. But what we can put in is we can put in all of the points essentially that satisfy this relationship. Is it going to be inside or outside of this circle?
Inside.
And is it going to be, what's the radius going to be?
2.
Good. So I'll use dotted lines to indicate going into. That's not bad. Okay. And so we have this circle. If you catch my drift, I know that's not the greatest thing in the world, but this has a radius of 2, so this would be 2, it'd be 2, it's -2 back there, -2 back there. And so all of this set of points in the plane, that is what we're allowed to input into here. So now we're representing a domain actually as kind of a region. We start calling it a region if it's understood that we're doing it is in R3. Versus, and compare that with the 2-dimensional version. If I just said y is equal to the square root of x. Okay, well, that's different. Because then in only 2 dimensions, that tells me that I just have to choose non-negative x values. So I could essentially take this, right? And so this becomes essentially the shaded domain. It's just that when we have a 2-dimensional plane, there isn't much to see except for what we're allowed to put in. So that interval is a little bit more boring than describing this set of points, which actually can be a region.
How exactly is that circle oriented? Is it perpendicular to the XY plane?
No, imagine it's just a circle that's laying flat on that. Yeah. Yeah, so imagine if there was a camera angle, so if you were sitting on top of the arrow right here for the z-axis and you were looking straight down on it like that, it would just look like you had graphed a regular circle in the R2. Yeah, in R2. Okay, let me teach you how to describe this using math language now. This is a set of points, and so we use the curly brackets to indicate this is a set. Now, the kind of point, these are ordered pairs, x and y. Ordered pair, x and y. That's the kind of points that we're describing. Now it's not every single ordered pair. And so that colon means such that. It's going to now put a restriction on this. And it's specifically the ones that satisfy the relationship x squared plus y squared is less than or equal to 4. And if you really wanted to be super precise, what you could say is you could say ordered pairs x, y, a member of, that's remember what that means, a member of R2 to specify that x and y are actually real numbers such that x squared plus y squared is less than or equal to 4. So you could do it like that if you're feeling really spicy. The extra credit won't be necessary because if you pay that much attention in math class to the little details, your grades will be good enough anyways. Does that make sense?
Yes.
Okay, so that's start getting used to building set stuff because if you don't start practicing now, when we get to double and triple integrals and regions and such, your brain's just going to be vomiting on you all the time because you won't even be able to set your problem up, much less get to the integrals. Okay, so this language of math it's not complicated, you just got to be familiar with it. So expose your brain to it early on. By the time you get there, it'll be much easier to pick up. Okay, questions about that example?
Less than or?
Less than equal to. Yeah.
So what's the major difference between the two sets? So you're explaining.
Oh, between these two things?
Like you explained, you are stating that it does belong to R squared. How does that impact the set itself compared to not specifying that?
Very good question. First thing, don't call that R squared, call it R2. Second thing is these mean pretty much the same exact thing.
Okay.
This is more specific.
Okay.
So if you were doing like an abstract algebra class, when we don't actually assume real numbers is a very specific assumption. So this is conventional to do in engineering calculus 3, because in engineering calculus 3, you're interacting with real numbers for the real world. And so you could just say this and everyone on planet Earth knows exactly what you're talking about. They're not going to think to that, oh, is X and Y potentially the elements of like the group O2 symmetric with it? No, it's just going to be reals. And this is if you really, really want to specify that these ordered pairs are in R2.
And R2 is real in 2 dimensions, right?
Yeah, basically R2 says X will be a real number and Y will be a real number. And then these are real numbers. This can be useful, so sometimes you might want to restrict this. Maybe you don't want all the real numbers. What if you only want the integers? then you could specify that. So that restricts X and Y to only being integers. Or you might want only positive real numbers, only negative real numbers. That's where you could specify that. But in general, the assumption is you can just use this. I'll understand, everyone will understand you're talking about real numbers, X and Y, and then the restriction. Okay. There's kind of one more, there's only really one more definition that's important for this. That's a little different than Calc 1 per se. Because with surfaces, okay, I want everybody to imagine an anthill in their mind, okay? And now if you were to take like a piece of cardboard or a flat paper or a flat metal sheet or something, and then just slice somewhere through that anthill, okay? Now, if you were to trace the boundary of the anthill slice that you took onto your sheet and then pull it back out again, you'll have a graph of something. And so we're going to give that a specific definition because those kinds of curves that can be generated by horizontally slicing through a surface are kind of important. You guys know what topography is?
Yeah.
Yeah, okay. How many of you have gone to, say, like a national park where they had mountains or like they're giving you the different things like that? So you see the elevation and they'll say, okay, on this mountain, then you'll see all those random little squiggles that are kind of like surrounding things, and it'll tell you the elevation for that particular line that goes around. That's basically what we're going to talk about right now, Kelsey. Those are level curves. In other words, lines that show you how tall, at what elevation you are, and all the points that have the same shared elevation. So there's two things, contour curves and level curves, that are related. So let's define those. A contour curve is the intersection of a surface. So regardless of what that is, a surface. And again, like that sheet through the anthill, a horizontal plane. And it's going to be, we're going to choose some constant z naught. And so we're going to fix z at a certain height that we're going to slice through our surface. And that intersection of points, basically, along the plane and the surface, is what we call the contour curve. And then what we can do is if we project, so projecting a contour curve down onto the xy plane, because again, when you slice that at the height z naught, that curve and the intersection is existing somewhere, not necessarily restricted to the xy plane. And so if we're only interested in its top down, kind of like a bird's eye view, that's the level curve. So that's the distinction. Contour curve is whatever you get when you do the slice in 3 dimensions. But then what we're gonna do, we project it down, analyze this, it's gonna be more useful. This is where we get topographic maps. This yields, so projecting contour curve on xy plane yields, and you can actually directly calculate this, right? So if you have fxy equals that fixed constant, whatever height you're supposed to have. And so this curve in the xy plane is what we call, is called a level curve. So while you're writing that down, I'll set up a kind of a visual example here. X, Y. I'm evolving. That looks actually semi-readable. Okay. Got it. So that's okay. Get the idea of what's going on here. So we've got some sort of a surface. Now, let's fix a very specific z naught. So let's choose some z naught to be this height, right? This will be our z naught. We take this horizontal plane, And see if I can not mess my drawing up. So we've got this plane kind of cutting through. And so the intersection of this sheet that's cutting through this, our beautiful little Jello blob on the table here, is going to be some intersection. And so to easier see that intersection, I'm going to now do a camera shift. And instead of looking at it just from, as a whole, we're going to sit on top of this Z arrow and we're going to look top down. And so what we're going to see is an X, here's my Y, and we're going to see the plane. And that's going to be what's intersecting with the surface. So here's the surface, and then this is specifically what's being intersected. And so the actual curve up here that's being chopped out up here, that is which one? Is that the contour or the level? Yeah, it's contour. This one has this yet been projected down onto the XY plane. Now this is still up with the original surface. So this is the contour curve describing that fixed elevation of Z naught. So say you're trying to do a hike and you're looking at the stats for the hike and you say, okay, we're going to gain 450 feet in elevation, and at this specific point, we can walk around this part of the hill and we're going to be at like say 250 feet. What about this curve? What do we call that? That's the level curve from the contour curve that we chopped out at this height. That makes sense? So this box that I drew is representing that plane Z is equal to Z naught, and it's chopping off this, and we've just top-down view now, looking down onto what that is. Now, what's really fun, I think I'll have you do this in the next lab, is you can generate your own topographies on surfaces just by slamming in different constants, Z naught, and then computing what curves result. So it's like if this is X, this is Y. If we take a whole set of a bunch of different contour curves and then project them down into a bunch of level curves, at the very, very tippity top, it's going to be just like a little slice, right? Not much there to intersect. Say I start walking down the hill. I'm going to decrease my elevation a little bit. What do you think is going to, what size is going to happen here?
Bigger.
Yeah, it's going to get bigger. So now we're lower in elevation and there's more points that are at that lower elevation. What if I now decrease down to this height? Is it going to increase the size or decrease the size of the circle? All right, so now we're at a lower elevation. And as we continue to go down, we can continue lowering our elevation. So this is how you can tell how steep something is. Because usually they'll give you the increments of your decreases in Z naught, they'll make that a fixed rate. So you'll go down by say 10 feet, then 10 feet, then 10 feet.
The more lines there are, the steeper it is.
Exactly. Because if you're suddenly dropping off, then that means you've increased a lot of height in a shorter amount of time. So this is a pretty even slope, right? This would be the difference between the rings here isn't too pronounced. But if you had something that was like this, like right? So that's like it doesn't grow much at all, and then suddenly you increase it by 10 and you're ripping up in height at a really, really fast rate. Or so there's all sorts of different things you could do with this. You throw rocks into water, all the males in here have done it. And for far longer than we're willing to admit. And but essentially when you drop that into the thing and those ripples are coming out, essentially you could find all of those little all the level curves in your water. So lots of applications of this stuff, but is able to visualize what's going on? I know this is difficult to write on the whiteboard, so I was trying to find a way to potentially to help ease the concept without three-dimensional models. Yes.
So is there an equation for the curve that we also got to know that could impact that behavior?
Good question. Let me see if I put I have an example for how you would apply the computations.
Is it like use this like as a rough method to kind of find the domain depending on how the shape changes? Does that make sense? Like,
You could. I think the domain will always be easier to find just directly from how the function's been defined. Yeah. But in theory, yes, it'll agree. So you could work backwards if you want to. Okay, yeah. I'll go through an example of how you practically generate these level curves from an actual function. So example. The level curves. Of a function that's given explicitly as y minus x squared minus 1, okay? So here's how we do this. The level curve is we're going to project it by just choosing some fixed z value. So let's choose z is equal to 0. Okay. So if we have that horizontal plane, how does that intersect with our thing? Let's plug in 0. 0 is equal to y minus x squared minus 1. And if you're to rewrite this into what you would expect this to be, this is y is x squared plus 1. So this particular level curve, I'll generate them over here. Here's x, y. So y is equal to x squared plus 1. Okay, so that's a parabola that starts here and it goes out. So this is the level curve for z is equal to 0. Fair enough? Now, what if let's see what happens as we go up this surface. So z is now equal to 1. And put 1 in here. 1 is equal to y minus x squared minus 1. And when you rearrange that, you get y is equal to x squared plus 2. Okay, so when we increase the elevation now, top down, the surface is going to here's the next. That's the 1. Interesting, right? And you can probably imagine if I keep increasing this, you can just check it for yourself, we'll generate more level curves that just keep coming up and up, etc. So if this is the top-down view, then you can imagine that if you were to kind of pan out, you've got this interesting horseshoe kind of shape, like an iron, that's rising with a slant, right? So it's getting taller, but as it gets taller, it's not staying in one location. It's gradually shifting up in that positive y-axis direction. So that's how you can practically. There will be a lab question on this. You'll get a chance to visualize and generate these on your own. But all good?
Yep.
For the level curve, sorry.
Sorry. We got to see.
What? Oh, you got it. Okay. Keeping a lecture clock is something that I used to not be as good at. It's like textbook. All right, last thing, we're gonna extend the concept. If notation, so from pretty much the first lecture, I said, all you're doing is you're extending the idea. We're not coming up with completely new stuff. And so here's our notation, right? So we started with our good old y is equal to f of x. And implicitly, we give that by fxy, and then we understand that this is going to exist in R2, right? Fair enough. So this is where we start. Now let's extend the idea. 2z is equal to f of what?
XY.
Xy. And so implicitly, that's what? And what is this going to exist in?
R3.
Now, rocket science, but what if we just did w is equal to f of x, y, z? So now the actual input is a point in all three-dimensional space and a four-dimensional graph. So we can no longer see this anymore. But how would we do that implicitly?
X, Y, Z, W.
And then what's this going to exist in?
R4.
And so now when people say all those, you read a stupid BuzzFeed article on like, oh, scientists found the fifth dimension. No, they didn't. They just discovered one day that we can represent a graph with more than one variable, and ergo now it has more than 3 spatial dimensions. Okay, so why on earth do this? Well, what if you want a 3-dimensional space, but say time, or maybe not time, but the temperature of your surface, depending on where it's at, the density of your material, depending on where you're at, the speed of the wind, depending on where you're at in the song, you know, the air pressure being exerted on your submarine jokes might be insensitive. Okay, when you're going into a rocket, right? So the pressure on the top of the cone when you're combating atmospheric forces. So things like that, you can have non-spatial dimensions being expressed by having these. So you can have as many of these as you want. So we're going to extend it to xn plus 1, explicitly being x1, x2, up to n inputs. So you can have any kind of variables, different things you could measure, things you could be interested in and model with a function. That's a lot of information, and you can have a ton of information, and implicitly, you would just have the set x1 all the way up to xn plus 1. And then what would this be? What quote unquote space is this going to be in?
RN.
The debate's going to be, is it Rn or is it Rn plus 1? Yeah, and plus 1, because that's how many different variables or parameters we've got going on here. So you can have something. Here's kind of my favorite illustration of that. So when you guys can no longer say, oh, it's not rocket science, because this is rocket science now. So here's the tip of, say, they're testing the tip of a cone. And they're going to use this material to be on the top of, say, like a rocket. Okay, and so when they do those blast chamber tests and they stick it in front of a thing and they just, see how much it can take. They could measure lots of things. So first, they've got to identify which point on your cone we're talking about. So they're taking data and they have computers that can take lots of data, and they're interested in, say, like this very specific point right here. Well, that is a point in 3 dimensions. So they need to accommodate for 3 spatial dimensions of where you're at on our cone that we're trying to test. But they might be interested in another variable, maybe P for pressure, or P for temperature. They might be interested in D for density of the material. And then other physical parameters that could be all associated as data with respect to that particular point on the cone that isn't spatial, but you could still turn into a function x, y, z, p, p, d. Now, the graph of that isn't really the point. The point, though, is that we have a way to describe what we're interested in, not necessarily in spatial dimensions. So that's the extension now of functions to multivariables. Welcome to multivariable calculus, right? This is the upgrade from what we've been doing in Calc 1 into talking about calculus and rates of change with several variables. So, any questions about this before I hand out exams?
So just to confirm, you can add like pressure, temperature, and they all in together in one, or do they have to go in one certain?
Well, they don't have to be. So they can be completely separate like this. So it's like in the same way that when I choose a random point in space, x, y, and z, those 3 spatial dimensions aren't necessarily functions of each other. It's just that there's a point. Here's its x coordinate, here's its y coordinate, here's its z coordinate. So it's like giving its address and all the characteristics of that. Yeah. You can choose, there's a very interesting set of recursive functions and other things where each individual kind of component can be then parameterized as functions of other components. But that's parameterization that we'll get into, I think, later. Yeah. Any other questions on this stuff?
Considering some real world functions and real world units may be dependent on each other, but not all of them depend on one. Is it possible to model this where, say, 2 of the 3 would be modeled on one, but the others wouldn't?
Yeah. Okay. We'll get into that when we do parameterizations on surfaces with S's and T's, U's and V's, and it gets all crazy and everyone vomits because Jacobians are ugly and etc. But yeah, you can do pretty much anything you want. Done. Okay, cool. I'm gonna pass out. The nice thing is, if we start early,
Yeah.
then you guys can technically be here. Well, let me stop the recording here first.